This is section 1.1, part B. Now that we've talked about what it means for a relation to be a function, we're going to talk a bit about the notation that we apply mathematically. If I have a relation like y equals 2x plus 5, we'll consider x to be our independent variable and y to be our dependent variable. And the function rule says take the input, or x, multiply by 2, and then add 5. Now, we don't really want our readers to always have to think about, hey, is this a function or isn't it a function? So if we already know it's a function, we sometimes just give it new notation. We give our function rule a name, often f, but we can name it anything we want. So to rewrite this equation using function notation, I would replace the y, the dependent variable, with the notation f of x. Notice that this notation tells us several things. First of all, the name of the function is f, and it is a function. We don't have to wonder, we don't have to test. It is a function. Secondly, the input variable will be x. So that one function notation tells me all of that. The other side then just basically gives me the function rule. One really important note, in this notation, again, this f parentheses x is read f of x. We're saying f is a function of x. The parentheses don't indicate multiplication like they often do in other aspects of math. All right, since f of x and y both occupy the same position, right, in these equations, they really are interchangeable. And sometimes we even write this, y equals f of x equals whatever our function rule is. In this case, 2x plus 5. What are some other advantages of function notation? Well, watch how easy it is if I want you to plug in, substitute a 1 for x. If all I have is the y equals notation, I actually have to write down, find y when x equals 1. And of course, it's not difficult to do. You just substitute the 1 in for the x. And 2 plus 5 gives us 7. If I want to do that same exact problem, but I have function notation, it's actually much simpler because all I have to write is f of 1. I've now told you wherever the x was, I want you to put in a 1 instead. So literally replace the x with a 1. That means when I get to the when I get to the x on this side, I'm simply going to replace it with a 1. And of course, we're going to end up with the same answer, 7 again. But really convenient notation when we're trying to say, hey, plug in a value for the independent variable. Let's practice that a little bit on the next page. In this example, we'll stick with our original function f of x equals 2x plus 5. And now I have a new function, g of n, equals n squared minus 2n minus 4. Notice the name of this function is g, and the independent variable is n. That is, the variables on the side are all n's. All right, our first problem says find f of 3. I'm going to go to the f function and replace the x with a 3. That would give me 6 plus 5, or 11. In number 2, I want g of negative 5. So I go to my g function, and I replace the n with negative 5. So first of all, this n becomes negative 5 squared. And you'll notice that I did put the negative 5 in parentheses. That's really important when you're substituting a negative number. It's always best to put it in parentheses so that you don't get the negative separated from the value of the number itself. All right, minus 2 times n, there's that n again. So I'm replacing with my negative 5 in parentheses, minus 4. Just following my order of operations, squaring negative 5 times negative 5 is 25. And then doing the multiplication next, I'll end up with a plus 10, and then a minus 4, which gives me 31. By the way, your calculator is perfectly able to do order of operations if you've got like a TI-84, a TI-Inspire, any of the fancy calculators. If you type your expression in exactly the way it looks, just like this, your calculator should give you the correct answer of 31. In fact, you might even want to pause and try that if you haven't already. All right, in number 3, we're being asked to find f of a. All I'm being asked to do here is to take the x and replace it with an a. So there's almost no work to this one. I just replace that x with an a. I have 2a plus 5, and I'm done. There's nothing more I can do. Number 4, g of 4x. So I go up to the g function, and every place I see an n, I'm going to replace that with 4x. So again, I'm going to use parentheses here, 4x squared. It's not just the x that's getting squared, it's the whole thing, the whole 4x. Minus 2 times, replace the n with a 4x, and then minus 4. If I simplify this one just a little bit, 4x times 4x would be 16x squared. And then I'd have a minus 8x and a minus 4. And no more like terms, so that's as good as that one's going to get. All right, a couple more. In number 5, we want f of 7w squared minus 1. So once again, I go back to f, and maybe I should just write f of x right above here because it's off the screen at this moment. Instead of this x, I'm going to replace the x with the whole 7w squared minus 1. So 2 times 7w squared minus 1 plus 5. I can do a little bit of simplifying here. I'll distribute the 2. So I'd have 14w squared minus 2 plus 5, and then combining my like terms, 14w squared plus 3. One more. I'd like g of 2x plus 3. And again, let me just remind you, g of n here was n squared minus 2n minus 4. So everywhere I see an n, I'm going to replace it with 2x plus 3. So right from the beginning, 2x plus 3 all gets squared. Again, notice those parentheses are super important. Subtract 2 times 2x plus 3 minus 4. All right, there's a really common mathematical mistake that we want to avoid right here. This 2x plus 3 being squared. It really means multiply 2x plus 3 times itself. And notice that that's going to require, sometimes we call it a double distributive law, or you might consider it the FOIL process, right? But we have to multiply 2x times 2x, it's 4x squared, plus 2x times 3 would be 6x, plus another 3 times 2x is 6x, and then finally 3 times 3 is 9. So we want to make sure to get all of those terms in there. It's really easy to miss the middle two. All right, distributing the negative 2, I'd have negative 4x minus 6, and then a minus 4. Bunch of like terms to combine here. We have 4x squared, and then I've got 6x plus 6x minus 4x. 12 minus 4 would be a plus 8x. And then I've also got 9 minus 6 minus 4. 9 minus 10 would be negative 1. And there we go. All right, one more thing about this function notation in this particular section. So far, all of our examples have specified the value of the independent variable. I've told you what to substitute for that independent variable or input. It's also possible to be given the value of the dependent or output variable and then have to solve for the independent or input variable. We'll take a look at that in this next example. We'll have some new functions here. H of x will be negative 3x plus 7, and k of t equals t cubed. Notice this told me the independent variable was going to be t, and indeed it was. All right, in example 1, it says find x if h of x equals 10. So I'm actually going to take this 10 this time and literally replace the whole h of x with 10. 10 equals negative 3x plus 7. I now have a little equation to solve, so I'll subtract the 7. 3 equals negative 3x, and then dividing by the negative 3, turns out x is negative 1, and I've done what they said. I've found or solved for x. In number 2, we'd like to find t if k of t equals 8. So again, I'm going to take this 8 and I'm going to replace the entire k of t with 8. So 8 equals t cubed. T would be the cubed root of 8 or 2. And I've found that t value. Couple more. In number 3, we're to find t given that k of t is negative 1,000. So I'll replace my k of t with negative 1,000. That will equal t cubed. T then is the cubed root of negative 1,000 or negative 10. By the way, notice cubed roots are okay to take when we have a negative value, but not square roots, right? Last one, find x if h of x equals negative 15. So I'll replace the h of x with negative 15, and that's equal to negative 3x plus 7. Once again, a little bit of an equation to solve here. We'll subtract the 7. Negative 22 equals negative 3x, and we'll divide by negative 3. That doesn't come out evenly, and typically in algebra we prefer an improper fraction to a mixed number. So I'm just going to leave my answer as the fraction 22 thirds for x. You've probably seen this already, but if you haven't, just a reminder that in my math lab, if you're doing homework, be careful. They'll usually tell you whether they want a decimal or a fraction for an answer. I'm leaving this answer as a fraction, but if my math lab had said, give me a decimal rounded to 3 decimal places or something, of course I could have divided that on my calculator to get the decimal approximation. What's nice about the fraction, though, is it's an exact answer, so I'm going to leave it at that. All right, this concludes section 1.1b.